for our last talk of the session, Cooper is going to present understanding accuracy efficiency trade-offs as a means for holding distributed ML systems accountable.
Hi there, I'm Cooper, and I'm a PhD student in computer science at Cornell University. And today I'm going to talk about a position paper with professors Karen Levy and Chris Dessau, which argues that understanding trade-offs between accuracy and efficiency in computing can help provide a mechanism for holding distributed machine learning systems accountable. Before diving into the details, I'll begin by outlining the broad strokes of the argument that we make in our paper. In short, we argue that policymakers are used to reasoning about accuracy efficiency trade-offs. In fact, they already do so in highly technical areas like public health. Therefore, since such trade-offs are particularly relevant in computing, they should be similarly useful for the governance of computer systems. To make this case, we choose to focus on real-time distributed machine learning systems, with the concrete running example of autonomous vehicles, or AVs. We do this for a couple reasons. For one, understanding the policy implications in this area is particularly urgent. By some measures, AVs are already here, and they are high stakes and safety critical. While AVs seem to promise to improve overall car safety, they will also create unprecedented risks. This is the second reason why we focus on AVs as our example. We show that some of these risks result directly from the accuracy efficiency trade-off and the choices made to implement it. More generally, we emphasize distributed systems because much of the socio-technical conversation in machine learning has dealt with algorithms, notably in discussions of algorithmic fairness. This is less systems components, things like scalability, speed, and their impact on correctness. Scalability, speed, and their impact on correctness, generally underexplored in terms of technological accountability. Keeping this in mind, I'm going to start by providing some intuition about the fundamental tension between accuracy and efficiency. There are many possible ways to optimally balance between them. This trade-off curve shows that there's a spectrum between the two, and optimal implementation choices require picking a point on this spectrum. Let's make this concrete with an example, the approval of COVID-19 antibody tests. About a year ago, the World Health Organization argued that prior to certifying COVID-19 antibodies as a possible treatment, it was necessary to guarantee that antibodies conferred immunity to the virus. That prior to using antibodies, we needed to be certain about their accuracy as a treatment. Numerous medical professionals challenged this mandate. In a letter to the New England Journal of Medicine, they argued that this approach biased way too strongly toward accuracy and away from efficiency. Paraphrasing their argument, they said that in the context of a raging pandemic, we do not have the luxury to gather all relevant evidence. Failing to take an action is itself an action that carries profound costs and health consequences. Importantly, regardless of how doctors would specifically choose to balance this trade-off, their overall goal was to reduce harm. To assess which harm is greater, that of deploying potentially inaccurate antibody tests or waiting to deploy them when doing so earlier could have helped avoid more harm. At a high level, we are making the same decision when choosing how AVs will make decisions to reduce bad outcomes. We want to reduce bad outcomes, and in the process, AVs will have to balance collecting accurate, complete information to make decisions and making decisions efficiently enough for them to be useful. To not take so long to make a decision that an accident happens anyway. What is notably different between these two examples is that AVs will be operating at much higher, potentially sub-second speeds. This will become clearer in a bit when I talk more about AVs as an example of a distributed machine learning system. For now, I've talked about these examples because they show that accuracy efficiency trade-offs are a useful and natural way that policymakers regulate complex domains like public health. In our paper, we therefore ask, why not use this framework for making policy concerning distributed machine learning systems? The specifics of the domain may vary, but reasoning about such trade-offs and their relationship to risk is not a new problem. So if we can reason about underlying accuracy efficiency trade-offs in emerging technology, we should be able to better assess and manage the risks they present. And we already have some techniques for reasoning about such trade-offs all over computing, including in machine learning and in distributed computing. In distributed systems, a network of computers works together to solve problems. Each computer has its own data and performs its own computations, communicating and sharing information with other computers when necessary. This communication takes time, impacting efficiency. There are also issues of accuracy between computers. Each computer has its own data, its own view of the state of the overarching system. That information is not complete. It's just a subset which can conflict with the views of the other computers in the system. So in short, there is a trade-off between all of the computers in the system having the same accurate understanding of the data in the system and the time it takes to communicate that understanding throughout the entire system. We get to choose how much communication happens between computers, decide how much time we spend sharing data in the network, and how accurate each computer's view of the overall system is. While we have tools to measure this underlying trade-off in distributed computing, we don't really have similar tools to measure out these underlying trade-offs in existing distributed machine learning systems. We talk in more detail in the paper about why this is the case, but the important takeaway is that distributed machine learning systems raise different accuracy efficiency questions than either distributed systems that do not involve machine learning or machine learning systems that are not distributed. Since machine learning models necessarily approximate the world, it is possible for them to operate on data that are not completely accurate and still yield results that are correct enough, that fall within some bounds of imperfection that we deem tolerable. This is also true in distributed computing. We can do less communication to increase efficiency, decreasing accuracy between computers in the network, and the overall output of a distributed computation can still be correct. But existing techniques in distributed machine learning systems do not guarantee overall correctness. Even if we can assess and guarantee each machine learning and distributed systems component individually, this does not necessarily translate to meaning we can do so for the global overall system. And this is going to be a huge problem for safety critical systems like AVs, which need such overall behavior guarantees. More particularly, an AV can be thought of as a distributed system of sensors. Each one has its own local information about the environment, but may also need to take time to communicate with other AVs that have useful information nearby. And yet, AVs are also going to have to make decisions quickly, in some cases, necessarily using inaccurate or uncertain information. And given these conditions, we want to be able to guarantee, at least with very high probability, that these decisions are correct. This means we need tools to analyze the underlying accuracy efficiency trade-offs so that we can reason rigorously about their implementation of the trade-off and how it relates to overall system correctness. Based on these challenges, we propose that computer scientists must build such tools for reasoning about accuracy efficiency trade-offs. In the paper, we describe this in more technical detail and suggest concrete areas for future research to create these tools for distributed machine learning systems. We then go on to argue that policymakers should use these tools to assess trade-off implementations and incorporate these assessments in their analysis of risk. This way, they can meaningfully intervene to ensure implementations align with public values. I want to emphasize that these calls to action are urgent. They aren't just something we need for some imagined future. The 2018 Uber crash in Arizona demonstrates this. In short, the AV did not have adequate mechanisms in place to make a correct decision fast enough. The AV did have algorithms to detect pedestrians, but when its multiple sensors actually had to do so in this case, they had a conflicting view of whether there was a pedestrian in the AV's path. The AV spent 6 seconds trying to resolve inaccuracies across its sensors, and in that time, arguably a really long amount of time for a computer to resolve inconsistencies, it collided with and killed a pedestrian on an otherwise empty road. In other words, the AV made a choice that was neither accurate nor efficient. The tools we recommend in the paper help avoid such suboptimal trade-off implementations. They will help foreclose some bad behaviors before they occur. But as with all complex systems, accidents will still invariably happen. By exposing a way to reason rigorously about the trade-off, these same tools would help policymakers analyze accidents after the fact in terms of accuracy and efficiency. For example, they could pose and answer context-dependent questions around when it is safe for a system to spend more time computing decisions, particularly when more efficient heuristics do not sufficiently remove uncertainty. So to wrap up, I want to highlight that this kind of approach to technological accountability that I've discussed today relates more broadly to extracting higher level values from technical systems, values like safety, as a necessary part of public governance. Specifically, our paper focuses on how we can make accuracy efficiency trade-offs in distributed machine learning systems transparent to policymakers, so they can make sure that such systems align with overarching values that we want to promote in policy. Using the tools that we recommend, policymakers will be able to perform more robust risk assessments of technology like AVs, and will be better equipped to determine the scope of possibilities for its governance. Thank you. You can find me at this link, and I look forward to your questions.
Thanks for a great talk. Any questions from the audience, please type them either in the chat or the Q&A. Okay. I have a question, and I'll be a little bit stubborn because you started by saying that we shouldn't just be thinking about fairness, but I couldn't help but think about the fact that these accuracy efficiency trade-off that you're discussing could also be a useful way to, in some cases, reframe what we often talk about as the accuracy fairness trade-off that arises in some cases. And I was wondering if you had any thoughts of how your approach could be useful in helping us think about this.
Yeah, thank you for that question. I have a very long answer to that, and so I will try to make it very short. I think that we wanted to emphasize in our paper the distributed systems aspect of this, right? So a lot of the fairness conversation, right, is around machine learning systems that don't involve the same sort of time resolution, very small time resolution that things like AVs and high index systems like that will have. And so this paper is really about that, and the techniques that we suggest really sort of align with that distributed sort of high-speed systems in particular. I think you're right that more generally, you could potentially frame the so-called trade-off between accuracy and fairness in other ways. I'm not sure that this formulation works so well for that, but I'm also someone who actually believes that trade-off is sort of has some tautological reasoning in it, and I've actually written about that in other work. So I would hesitate to try to transfer this to that domain.